Hello everyone, I'm back today for Coding Everyday Day 10. We're going to look at another linked list problem. Feeling good today, so today is Saturday, January 25th at 4:36 p.m. So I'm trying to complete this neat code roadmap. So yesterday I did I did copy list with random pointers. I started doing this one off camera, and then so I'll do find the duplicate number for this episode today. So let's get started. So you're given an array of integers num containing n plus 1 integers. Each integer in nums is in the range of 1 to n. Every integer appears exactly once, except for one integer which appears 2 or more times. Return the integer that appears more than once. Okay, so the recommended is O of 1 space, which is the tricky part, and O of n time. And without modifying the array. Oh, we're given the array. Oh wait, so we're supposed to use the linked list to solve it? Okay, so if I print nums, so this is just a list. It's not a linked list. Huh. Okay. So nums contains n plus 1 integers. Each integer in nums is between 1 and n inclusive. So for instance, if you have n equals 5, then you have the length is 6. And each one can be between 1 and 5. Okay, every integer appears exactly once, except for one integer which appears 2 or more times. Okay, so there must exist, so for instance, if n equals 5, we should expect 1, 2, 3, 4, 5 to all appear, and then one of them can be duplicated. So this... Okay, but you don't necessarily have to go from 1 to n, because here n is 4, and we have 1, 2, 3. Here n is also 4, and we have 1, 2, 3, 4. So you could also have like 0, 0. Well, it has to be 1. So you could have like 1, 1. Huh. Well, okay. Because of its uniqueness, you only have so many slots that can be unique. You have n unique slots. So for instance, you have 1, 2, 3, 4. So you have n unique slots. So if you have something that appears twice, then you'll have n unique numbers and one number that appears twice. So if it's so if I say like number of duplicates and then like n unique, or like number unique. So the number of duplicates, if it's just 2, so like let's say 4 appears twice, I'm calling that 2 duplicates, then the number of unique is n. If you have 3, then it's n minus 1. And if you have 4, then it's n minus 2. So for instance, this has 3. So the number of unique is 1, 2, 3, which is n minus 1 because n is 4. It's also possible that you could have all of them. So you could have an array 1, 1, 1, 1 like this. That's a possible input, I believe. So can you solve this problem without modifying array nums and using O of 1 extra space? So constant space. So I'm thinking we could have different pointers. So we can't remember what we saw. So what are some truths about? They don't have to be sorted or anything like that, right? No. So I don't know how much we can determine with. So I'm. And this is under linked lists. So I'm wondering, like, do we have to create a linked list? Find the duplicate number, linked list, find the duplicate number. So am I supposed to create a linked list? So it's under the linked list category for me, which is a little confusing. So maybe I could just take it one step at a time and maybe just solve it with O of n space. I mean, obviously, if you solve it with O of n space, you would say, so using O of n space and not modifying the original list, you would just say visited, and this is O of n space here, so you would say for num in nums, if num in visited, print num, I guess just return num, else visited dot add num, so like that. So this works here, obviously, but we can't use a visited set. Hold on, I'm getting a phone call. All right, I'm back. So, all right. So with constant space, we can't have a visited. So I think we should use the fact that every integer appears once. So we might have to use equality somehow. So we have to use the fact that there's only one so if it's 1 to n, right? So we should start by finding 1 and then by finding 2 and then finding 3. Or so we can't store anything. thinking with like in linked list you can have like a slow and a fast pointer. I don't know if that could be relevant. So we'd start them here, and then the fast pointer goes here. So at every step we would check if there's duplicates. So the fast pointer goes here, slow pointer goes here. So 1, 2, 3. I'm kind of just guessing really, but I do know that we definitely have to use the fact that like expected behavior should mean that there's one of every there should be one of every number up until n. Okay, I also don't know how to solve the problem in O of 1 extra space. I honestly don't really see how this is linked list at all. Because how are we supposed to do O of 1 space? Because creating a linked list would be O of n space because we're creating a node for every element. So maybe it's just we can use principles in linked list or something. I don't really know why it's linked list. Okay, so let's think the positioning is pure random, right? Because you could have like 1, 2, 3, 2. You could have like 1, 2, 3, 2. You could have 1, 3, 2, 2. You could have like 2, 1, 3, 2. So if you had 2 pointers and you just checked like if any of them are equal, then that would be n squared. Maybe we could use like a sum or something. So I could do it in O of 1 space, but it would be n squared. So so like with just 2 pointers. So if we have like time and space. So I can do n squared time with constant space. And I can do linear time with linear space. But I need to do linear time and constant space. So we can't use any data structure. So we're just going to have to use like pointers and do comparisons to check that it's duplicates. And I don't think it has to be, let's see, so n, and each number is between 1 and n. And then it says n time and constant space. Okay, well, we know that the sum... Oh, wait, can we take the sum? Okay, okay. Yeah. So if we take the sum... So if you have 1, 2, 3, 4, right? So the sum of this is the Gauss formula which is n times n plus 1 divided by 2. So for instance, if we take the summation of I from 1 to n, it's equal to this. So for instance, we have 4, right? So we know that it would be 7, 9, 10. So it would be 4 times 5 divided by 2 equals 10. Okay. So if we take the sum of all the numbers, we know, so we could say like the expected sum and taking the sum is O of n times. So the expected sum should be n. So we'll say n equals length of nums minus 1. Well, yeah. So the expected sum should be n times n plus 1 divided by 2. And then we'll just return 0 to see the error messages. 10. So because it's 4, okay, but it gets tricky when you have more than one duplicate, but I can do it for one duplicate. So if we look at this case, for instance, which has one duplicate, it does this. So then we take the actual sum, which is just the sum of nums, and then actual sum minus expected sum will give us the answer. If there's one duplicate. So this should give us, 4. If there's many duplicates, so in this case, okay, so this works for one duplicate. So we get the actual sum. So I'll just call it actual and expected. So the actual is the sum. So let's look at the first test case, for instance. 1, 2, 3, 2, 2. 1, 2, 3, 2, 2. So the sum of these numbers is 6, 8, 10. 10. So expected, so n here equals 4. So n times n plus 1 over 2, which in this case equals 10. So for this to be true, so let me draw out a table, right? So if the actual sum so that means it's 0. So the difference is 0. So if the difference, let's do the other example first, and then we'll come back to this, because that one's a little harder. So I'm going to try to draw out a table. So it's 1, 2, 3, 4, 4. So here, the actual sum is 14. Right, the actual sum is 14. So if you take the actual minus expected, gives you the difference. So in this case, if the difference is 4, okay, so what would we expect if we got 13 actual? We would expect it should be 1, 2, 3, 3, 4, right? 1, 2, 3, 3, 4, which this gives us 10 and then 13. Yeah. So if there's one duplicate, so if one duplicate, then the answer is difference. Now let's think if everything's a duplicate. So if you have 2, 2, 2, 2, 2. So in this case, n equals 4 again. So expected is, so of just these numbers, is 10. And maybe I should take expected of n plus 1. So then what we could do is say what's missing. So that's another way to think about it. So let me just think about that. So it's like method 1, and then method 2 would be if you have 1, 2, 3, 4, 4, you could say, so actual equals 14, and you could say expected equals 5 times 6 over 2, which is 15. And then because you're missing 1, that means that you have 4 instead of 5, right? So if you were missing 3, so if expected's 15 and you have 12, you're missing 3, so that means you have a 2 instead of a 5. If the expected is 10 instead of 15, that means you have a 0 instead of 5, which is not possible. So then you can start thinking, well, I don't think it's possible to get 10, because then you would need, because if you have 1, 2, 2, 3, 4, and you couldn't have like 3, 5, right? That would not be possible, because each one is from 1 to n. Yeah, so it would have to be 4. So here you're missing 2 times 3, which is 6. So I'm thinking what you may be able to do is get the difference. So in this case, it's actually impossible, I think, because if you had 2 1s, then it would be 8. Okay, so in this case, the expected would be 15, but the actual is 2 times 5, which is 10. Okay, so basically you're missing, so you're missing plus 1. Well, this should be, so minus 1, 0, plus 1, plus 2, plus 3. That's like how much you would need to be to 1, 2, 3, 4, 5. So I did this ICPC problem that reminded me of this, where you have you calculate like an expected and figure out how far the actual is off of it. The only problem that I'm running into is there's a lot of combinations of what it could be. So I don't know if there's just a numerical way to tell. If there's one duplicate, it's pretty easy. Alternatively, we may be able to do a loop. So because we can get this in one pass, right? So then, given this, so given that the expected is 14, so let's say n is 4. The expected is 14, and then the actual is 10. then we know there's an extra 4. But where it gets tricky, so we still have where it gets tricky is when you have more duplicates. So here the expected is wait, I think I mixed these up actually. The actual is 14. So if we just use n, the expected here would be 10, because 4 plus 3 plus 2 plus 1, and the actual is 10, which is not good because there's an extra number. So this tells us that we need to find this number. So this tells us that the extra number is making us lose 2 because, and then the other method is the expected would be 15, right? 15. The actual is 10. I might be able to do it if I can sort it, but it doesn't say. It does say O of n, because if it's sorted, I think I could do that. But it says without modifying the array. Well, I guess if it's sorted, it's really easy because you would just. Yeah, the problem is pretty trivial if you sort it, actually. So. Okay. So if you rearrange these numbers into like 3, 1, 2, 2, 2, you could say that, well, this one gives us a -2. This one gives us +1, because that should be a 2. This one gives us, we need +1 here also. And then we need +2 and +3. So does this score mean anything? 5, 6, 7, 5, 6, 7, 5. So that's also the difference in expected versus actual, right? And then do you get the same score if you rearrange them differently? So this one is good. This one's good. This one's good. This one needs to be +2. And this one needs to be +3. Okay, so this might be able to work with this. Then if I have like 1, 2, 2, 2, 3. This one's good. This one needs 1. This one needs... Actually, this one's also good. This one needs 1. This one needs 2. So it should be 1, 2, 3, 4, 5. So this one also needs 2. Okay. So this also tells you the difference in... Okay, so if I do this, this will get me the second solution, but not the first one. And this one doesn't work because it returns 0, but it's actually 2. Okay, question though. If I have, for instance, 1, 2, 3, 4, 4, I should not also get 5, right? So maybe this number can tell us how many are wrong. So plus 0, plus 0, plus 0, plus 0, plus 1. So that gives us 1. Then we rearrange that. We have 4, 1, 3, 2, let's say like that. So this one is minus 3 plus 1. So 1, 2, 3, 4, 5 plus 3. So this also gives us 1. Okay, I think this is kind of getting somewhere, because here this value is consistent given this pattern, and here the difference is 1 because we're 1 away. So I predict that if I duplicate 3 instead, I should get 2 here. So this will be 0, and then this is minus 1, this is 0, this is 0, and this is plus 3. So now this gives us 2. Okay, so this is basically another way of calculating the expected value or whatever. So now I'm wondering, well, this is interesting to me because it seems, I don't know, it gives us some insight, because now we get these individual, where every position is off by. So what if I have 3 3s? So if I say 3, 2, 1, 3, 3. So the first one is minus 2. This one is 0. This one's plus 2. So 1, 2, 3, 4, 5. So now this gives us 3. So we know that with a score of 3, you could either have one, like, so you could either have 2 3s. Well, wait. With a score of positive 3 means that you could have 2 2s, or you could have three 3s. So could you have 1 1? So we could iterate through those. Well, no, that. So this score means how much we're off from, like, perfectly unique. And it doesn't use n. It uses, like, the length. So it's saying, like, here the actual sum is 12, but the expected sum should be 1, so 5, so 15. So we're off by 3. So that means instead of having a 5, because you can't have a 5. So instead of having a 5, we could have a 2, which means we have 2 2s. Instead of having a 5, to make the difference, we could have a 3 instead of a 2. which would give us +1. And we could have, so a 3 instead of a 1. Well, no, you don't need a 1, because you could have like 3, 3, 3, 4, 4, right? Okay, so now this would give you over the expected sum, right? Because, or for instance, if you have all 4s, so what do you do if you have all 4s? 4, 8, 12, 16. Let's say 20. But if n equals 5 in the Gauss formula, then it's 15. So here you're actually over by 4. So I could do it if there's one duplicate, but it's tricky because you also don't know which numbers the duplicates are replacing. So that's kind of what I realized. Like if you have 1, 2, 3, okay, yeah. If you have like 3, 3, 4, it's like this 3 could have replaced a 1, it could replace a 2, it could replace a 4. You don't know. Oh, well, you can't have this, actually. Wait a minute. You cannot have that, because then you have 2 duplicates. So this could be 2, which means, by definition of the problem, that these 2 would have to have replaced a 1 and a 5. Which means, so that sum that they've replaced is 6, and they've also replaced 6. So you could check 1 through n and check if any of those numbers are possible. I think I'm kind of getting somewhere with that. So if you have, so the first one, right? 1, 2, 3, 2, 2. So you know one of the 2's is legit, but these 2's must have replaced a 4 and a 5. So that's 9, and this is 4. So the difference now is 5. So you could say, so you have 9 and 4, or do you? No, you have. Okay, I think you have to calculate. So the sum is 6, 8, 10. And the expected with 5, like 1, 2, 3, 4, 5, would be 15. So let's check 1 through 4. So it has to be from 1 to 4. So that would be our n part. So with 1, for it to be 1, to get this much difference, 5 difference, we would have to replace a 2, 3, a 2 and a 3. So if we had 1, 1, 1, 4, 5, but we can't actually have 5 actually. So would it be 1, 1, 1, 4? And that would give us, well, if it was 1, 1, 1, 4, then the sum of that is actually 8, which is not what ours is. But what if we instead, so we need 2 more, so if we added in a 3, then the sum of this would be 10. Is that possible? So that'd be 7, 8, 9, 10. So how would we know that given this, it's not, all right, I'm back. So after I gave up, I looked at the solution. So I looked at these solutions down here, and so it has to do with like graphs and cycles, and it seems pretty confusing. But I did see one of the hints somewhere said it. So we can mark. So I'll try to implement a solution that uses that's O of n time and constant space, but it's going to manipulate the input array. So basically what we're going to do is mark something negative, and then if it's already negative, then we've been there before. So I'm going to try coding that. So if I whiteboard it quickly, so if we have like 1, 2, what is it? 1, 2, 3, 2, 2. So we're going to have a pointer I. Make it yellow. So we're going to look at whatever number is at index I here. So index 1. So we're going to go to the 1th index and mark it negative. Okay, then we're going to move I. Now we're going to go to the 2nd index because this is a 2. We're going to go to the 2nd index. So 0, 1, 2 and mark it negative. Negative. And now we're going to go, I is going to go up. So now this is a 2. So we're going to mark this one negative. But because it's already negative, it means that we've been there before. Oh, wait, sorry. This is actually going to bring us there because the indices are like this. So this 2 is going to tell us to mark index 2 negative, but because it's already negative, we've been there before, so we're going to return 2. So it's basically like you're just saying, like the negative is just like a visited. So you could say like 1, and then you could change this to like 2v, you know, and then 3v or something. And then you say if it has a v in it, then we've been there before, but instead of a v, we're doing a negative. Okay, so let's try coding that. So for I in range, I guess I could say for I num enumerates nums. I don't normally use that, so I just want to see if it's working there. Okay, looks good. So what we want to do is if nums, I guess we could just say if num, right? If nums of I is negative, then return the value itself at nums of I. No, at nums of I. Okay, so if it's not negative, so if this number that we're, or at the I value, so if it's not negative, then we say nums of I equals -1 times nums of I. And I think that's literally it. And then I think something has to, do I say raise exception or? Okay. All right, I don't know what I'm doing with that. Your output was none. Okay, so I starts at 0. If nums of I, so if nums of 0, actually we want nums of num, right? Yeah, I think that's what we want. Okay, okay. So we want, so I just goes up every time. So we want to check at the one position. So based on num. So if nums of num is negative, so if this one's negative, it means we've been there before. Okay. Otherwise, you say nums of num. I don't actually think we need I at all. Is that correct? Okay, that's what I meant to do. Oh, wrong answer. Okay, great. So what did I return? 3. Am I supposed to return nums of I maybe? Yeah, I'm supposed to return nums of I. No, I'm not. Okay, so let's see what test case it was, and let's trace it. So 1, 2, oh, sorry, submit. So it's 1, 3, 4, 2, 2. Like so. Okay. So we'll just iterate through it like that. So we could say for num and nums, I suppose. Or let's just say I. So okay. So we want nums at index nums of I. So I'm just gonna forget the enumerate thing. I mean, I guess it's fine. Nums of num. So nums at index num. So at index 1. And we want to set it to negative itself. Okay, and then I goes here. Now nums of 3. So we would say nums of num, but that doesn't exist. So we would need the absolute value, right? I think that's probably what's wrong. So we're trying to get negative 3. Equals negative. So we want to say nums of 3 equals negative nums of 3. So like that. That didn't work. So nums of 3 equals negative 1 times whatever that is, which should be positive. Yeah, because we would say nums of 3, 0, 1, 2, 3 is negative. So we want nums of 3 to be equal to itself. So can I just say times equals negative 1? Let me just print nums at every iteration. Okay, so it's 1, 2, 3, 2, 2. So 1, okay, I think I know the problem. So we don't want to know if this is negative. Maybe. So okay, so 1 makes this one negative. And then 2 makes this one negative. And then 3 is negative, but we don't care if. So it should make this one negative. So nums of negative. I think the enumerate might be messing me up. While I is less than length of nums. And then I plus equals 1. Because the way the for loop works might keep it going even if we change something. Okay, so 1, 2, 3, 2, 2. So 1 changes index 1 to negative. And then 2 changes index 2 to negative. And then 3 should change index 3 to negative. But it's not. So it's saying nums, but we don't care if this one's negative. We want to say the one that we're searching, because let's print nums of I. So nums of I is 1, so it searches here. But this part, so when I is 1, oh, is it because of that, the absolute value? So we want to search whatever. Yeah, okay. Is it because it's 1, 2, 3, which is negative? So I think it's an absolute value thing. Something here has to be absolute value. So the first one's correct, and the second time it's not. So when nums of I is negative, we actually want it to be positive. Like that. Okay, and now this one does not work. So I about 2, but it should be 4. Could it? No. So okay, so 1, 2, 3, 4, 4. This becomes negative, this becomes negative, this becomes negative, and this one makes this one negative. And then it should make itself negative again. Oh man, this is rough. Okay. So is this part correct? So if I think about it, right, if we have nums, let's just calm down. So nums is 1, 2, 3, 4, 4. Okay. So so I is currently right here. So I want to say nums at position, absolute value, nums of I. So at position 1. So I want to make So nums at absolute value, so nums at 1, right? Because this is 1 and then 1. So nums at 1, I want to make it negative. So nums of absolute value of nums of I times equals negative 1. Or let's just say, yeah, times equals negative 1. And now if that is positive, so if it's positive, is greater than 0, then we should return that number. We should return the number that we're at. We should return I. Yeah, we should return I. So we should return nums of I. Okay. We don't want to return this number. That was the problem. We were returning the number that was negative, but that we don't want to return the number that was negative. We want to return the number that brought us to that negative number. Okay. Pretty rough day with the code today. Yeah, pretty tricky. I had to look at the solution, and even after I looked at the solution, it took me a while. I wish I was getting these a little quicker, but I guess I'm still learning and everything. But yeah, so that was pretty rough. The real solution, it's called like Floyd's algorithm or something like that, and it uses, you basically detect if there's a cycle, and if there is, so you do this sort of stuff where you like go to the index of whatever number you're on, and then you detect if there's a cycle. But yeah, so I wish I was getting these quicker, and I wish I was understanding them more. But I think this is a really good practice, like environment practice, because like with technical interviews and take-home assessments and stuff, you can look stuff up. So by having it be a video, it kind of makes it so I don't want to look things up, and I just kind of test what I know and kind of think about it. So it's hard. I wish it wasn't this hard, but I guess I'm a little disappointed that it took me so long, but that's what practice is. And if you do it every day, it's not always going to be like 100% on your A game. So all right, so that's day 10. So I'll be back tomorrow for another video. I think so. I was doing this one so I could look at LRU cache, and then after that I got trees. I might try to look into trees a little bit so I don't just like have no idea what I'm doing for tomorrow's video. I know what trees are, but just in terms of like I've worked with trees, but just how LeetCode does it and like what sort of stuff it's looking for and everything like that. So yeah, that'll be tomorrow. I'll probably do a linked list problem or a tree problem. So all right, see you tomorrow for day 11.